SwayamPrabha. Digital India. Educated India.
In the beginning, there we came up with two techniques. One is a frequency domain analysis or the harmonic domain analysis. We went after doing that with eigenvalues and so on. Afterwards we did analysis in time domain, and we looked at not just normal mode, but what is the problem with having non-orthogonal eigenmodes, and then a lot of machinery associated with analyzing such a problem. But in either approach, whether it is time domain or frequency domain, we would need to supply a model for heat release, and that depends on how the flame responds to the oscillations, velocity or pressure oscillations around the flame. And in different combustors, this mechanism, that is how the flame or combustion process responds to the acoustic oscillations, is different. For example, in a rocket motor, the propellant will respond heavily to the pressure oscillations, because the pressure fluctuations alter the way the flame is standing above the propellant surface, and then it has a very strong influence on how the reaction rate is and how the mass flow fluctuations coming out of the pyrolyzed propellant is. Now, whereas we looked at premixed flame, where actually the pressure dependence is very weak, but it is mainly a velocity fluctuation dependence. Where you have velocity fluctuation, it affects the flame by some kind of wrinkling, and we also constructed a model by solving a kinematic model. We solved the G equation, we solved for the wrinkles, and we saw that the wrinkles propagated up, and there was a time lag associated with it. We actually derived expression for the wrinkle, and from there we can get the area fluctuations, and then we said that the area fluctuations translate to heat release rate. We also briefly spoke about diffusion flames, where in diffusion flame we said that the velocity fluctuations or the acoustic fluctuations affect the mixing between the fuel and oxidizer, and that really controls the way the flame is set up, and that leads to temperature fluctuations, and there is heat release. In premixed flame, it was more like the wrinkling which translated to area fluctuation, which translated to dilatation. So it is so in each case there is a different mechanisms, and many students asked me specifically about equivalence ratio fluctuations. So in the previous analysis we did not have equivalence ratio fluctuations. You can do the same premixed flame analysis with equivalence ratio fluctuations and what happens to wrinkles and so on, and there are many papers in the literature which works that out, particularly by the groups of Santavica from Pennsylvania State University and also Loewen from Georgia Tech. I would not look at that because it is in some sense a similar kind of analysis, but just same machinery you have to work out. But I will want to introduce the fuel flow modulation and airflow modulation that happens in a more practical combustor, which results in equivalence ratio fluctuations, and then we look at the consequences. Okay, so let me write down here. So normally we would say that in a combustor you are having the combustor burn at certain equivalence ratio. So what is meant by equivalence ratio fluctuations here? I mean, you set the fuel flow rate and set the air flow rate, and you have a certain equivalence ratio. So what is meant by equivalence ratio fluctuations? Can you try to imagine? And Viksha?
The fuel and the ratio of the fuel mass and oxidizer mass sort of varies, and it's not burning at
yeah, why is it? Why will it vary? Can you imagine?
The pressure fluctuations may pass on to the injector, and that may cause some it may sometimes reduce the mass flow rate of the fuel and sometimes increase it.
Yeah, absolutely perfect. So that's a very good answer. So when the this was let me, yeah, so in the 80s this nitric acid rain and sulfuric acid rain and so on were considered to be or people woke up to the fact that it is a big problem and they wanted to make combustors which will lower the nitric acid rain. Nitric acid rain means you have NO and NOx going up in the atmosphere, then it mixes with water vapor in the clouds and so on, and you have rain, and the rain has concentration of nitric acid or any other acid. So specifically we are worried about nitric acid here. So people looked at mechanisms with which NOx is formed and found out or started thinking about how the mechanisms can be taken advantage of and to result in low NOx oscillations. So what happened is people found that as you would burn under lean conditions, lean is fuel lean, I mean that is what it's implied by saying lean would mean fuel lean. So you have fuel lean combustors, that means you are there is also you cannot go as lean as you want. Why? There is some limit to which how lean you can burn. Yeah, below there will be a flammability limit below some limit for a premixed flame it won't burn. And you are trying to, so people try to do premixed burners under premixed burners have low soot production, and you can, if you burn them at low near the lean limit, you have very low NOx. That is what they found out. Now can you imagine why NOx would be low if you burn lean? Just one more thing. What happens if you have lean?
Low temperature.
Yeah, low temperature, absolutely. So when you have low temperature, so that's the correct thing. Low equivalence ratio will lead to low temperature. You can't go to, you can also have very high equivalence ratio, get low temperature, but then you are wasting fuel and there will be a lot of unburned hydrocarbon soot and all that. So we cannot burn rich, so we can burn lean. Now so why would NOx be low when temperature is low?
Nitrogen won't react.
Yeah, at low temperature the NOx production is less, so at least one of the ways of producing NOx is less. So people have understood that if you lower the temperature of the combustion, you will have less NOx. So wonderful, you proclaim that you have solved all the problems of the nitric acid and so on, keep all the environmental activists and left wingers happy, and then you make these combustors, and then some unintended consequence happens. What would that be? Instability. So when you go lower and lower limits, the performance of the NOx reduction, it's very good, but then the flame speed is starting to be a very strong function of equivalence ratio, and in the ignition time delay is getting bigger and bigger. So these now make conditions very conducive to form thermoacoustic instability. So that is what we will talk about. So let me first give you a reference for this. It is a very good PhD thesis. You can download it from so this is a PhD thesis done on the subject, so I mean a good slow introduction to the subject, but there are also a lot of papers on this, and I also have to give you some historical insight behind this. So the combustion instability research was very strong in the 60s and 70s, driven by what? Do you remember? Do you know? Space program and missile program. So the big rocket programs had a lot of instabilities, and then they made enough number of motors. So you try to make a lot of motors, but eventually have certain motors which are working, in which they somehow manage to solve the problem or minimize the problem or live with the problem. And then you can now run your program with combination of this number of motors. If you want to double the thrust, you try to make a big motor. If it doesn't work, put 2 of the old rockets, kind of like tie with a rubber band, not quite rubber band, but and if you want 4 times the thrust, okay, if you in case fail with a big motor, you can put 4 of the small motors. Somehow people found ways to get around it, because this is some subject nobody understands. So if you don't understand something, you generally would not feel inclined to watching. It's like watching an art movie or something you don't understand, or like a sports which you don't understand. So if you don't understand the rules, so the program managers have no clue what this thing is, so they are not interested in funding it, because this is always there, but they know somehow somewhere it can be fixed. So once it's fixed, you use those models. So what happens to the scientists who work on it? I mean, they are like, I don't know, there's this curry leaf, I mean, so after use you throw it out. So it's the kind of way it is, because this is a weird subject. It is not like a gas dynamics or something where you analyze, and from that with which you can go to propulsion, build a engine and so on. This is like, okay, if something blows up, I can tell you, or if it blew up, I can tell you why it blew up or something like that. So we are not doing anything. It's like a role of a policeman or something. First the robber has to rob, then you will catch the thief or something like that. And the policeman is not good enough to intimidate the robber and not make him rob. So this, I mean, so at least that's the state it is. And then the research went on a lull, and a few people still hung around there trying to do pulsating combustion, and they are trying to use acoustic oscillations to increase the productivity, and that kind of appealed to the managers, because he said, you can the combustion instability when it happens, your heat and mass transfer and momentum transfer increases, so creates all kinds of problem in rockets. But they said, okay, you take a cement plant, you put sound with a pulse combustor, and then make the droplets evaporate faster, or try to make milk powder evaporate faster to make milk powder, or some such or burn waste in the presence of high amplitude sound, and waste which would normally won't burn start burning because of the intense heat and mass transfer and so on. So a few people hung around there, had this subject of pulse combustion going and so on, almost getting out of business. And then came this activists who wanted to get rid of nitric acid drain, and then suddenly the combustion scientists woke up, and they were also getting kind of jobless with no new thing. So they proposed this low NOx things, companies bought the idea, made it, and bang, instability came, and then suddenly all of us got into business. We were almost losing our job, because it's like policemen losing job because there are no crime, and suddenly crime comes and then you are busy. So suddenly instability comes on and people are busy. So this thing got everybody going in gas turbines. So before, in the 60s and 70s and 80s, people didn't worry that much about gas turbines. So one thing was this NOx performance improving. Another thing is gas turbines, once you have an engine, they will improve this, improve that, and somehow get more and more megawatts out of the engine. So if some engine, if it starts giving 100 megawatt in the beginning, and then you tweak this, it will be 110. So there will be version 1, version 2, version 3, and then version 3 A, B, C, D, E. Finally you will have version 6 F or something like that, and by then this 100 megawatt will have gone to 180, 190 megawatts. So we are really pushing. It's like I told you, if you push somebody too much and they are performing very well, but then they can go crazy, or like a sportsman, if you push too hard, you can get injured right before the tournament. This is kind of what happened in gas turbines. They were there, but they were not performing to that level of performance in the beginning, but now they are performing at incredibly high levels of efficiency and incredibly high levels of low pollutants, and then instability stuck. So then all the guys who were who were closing their shops with rockets and so on, they came back to study instability in this, and thankfully the problem has not gone away yet, and so we are still in business. So I think it's important to understand how the technology evolves also, and someday this will be stopped, and I don't know what else comes at that time. So here we are I am going to analyze it, but since I am not I will not explain how to do the acoustic analysis because I already explained, and so what I will do is to concentrate on how the heat release rate has to be calculated or how the heat release rate is affected by the fluctuations, and then I assume that you know two different methods, one is a time domain analysis, one is a frequency domain analysis to solve for the acoustic field. Okay, so here we concentrate on the perturbations of heat release rate of a flame with particular emphasis to the role of equivalence ratio fluctuations. So everything is same, we have feedback between acoustic waves and heat release, and that is what makes the instability. There is no difference in that, the only difference is how the perturbation heat release is coming. So acoustic perturbation of velocity or pressure at the fuel injector, in this usually acoustic pressure at the fuel injector will fluctuate, and that will modulate the fuel concentration, and the velocity fluctuations will also modulate the airflow rate. Similarly, acoustic pressure oscillations and velocity oscillations will modulate the airflow rate. So therefore, we will have equivalence flow rate, equivalence ratio fluctuations. So this will lead to So you have inhomogeneities in equivalence ratio, and they are convected through the fuel air premixing section to the flame front where they modulate the heat release rate of the flame. So these equivalence ratio fluctuations are convected to the flame, and of course there is convection, so naturally there will be convective time lags also. So and we know that we love time lags. If there is a time lag, you have a chance of under some conditions things going unstable. So this is very significant in this mechanism is very significant in lean premixed pre-vaporized combustors. And I must emphasize that at low equivalence ratios near the lean blowout limit, the flame speed SL is a very strong function of equivalence ratio. So a small disturbance in phi can make actually a large disturbance in SL, which will lead to a large disturbance in heat release. Yeah. So I will draw a schematic of this combustor. So we will draw a schematic of a combustor. I am sure the combustor is, you know, it is much more complicated than this, but we have so this is the heat release zone. So there will be Q prime here, and there is phi prime coming here. Now subscript I denotes fluctuations at the inlet. That's it. So before I speak any further, I first want to ask you a very simple question. You have separate fuel line and separate air line, and I showed you a example of a combustor where you had a pre-mixed flame, and there we had a pre-mixer, then another mixing chamber to damp out everything, and then you had the tube coming, and it was absolutely pre-mixed. Why are we calling this combustor pre-mixed, although we have a air flow rate coming here, mass flow rate, I mean fuel flow rate coming, so the separate fuel and air coming, and why do you call it a?
By the time it reaches the combustion zone, it's mixed.
Yeah, so why don't you mix it in a big dabba and send it to the
It's, this is not only safety, this is in cases where axial combustors and all, we have air coming in, so fuel we have to mix on the way.
You can make a big box or big tank and mix a fuel air mixture, right, instead of having fuel cylinder. Huh?
Control the equivalence ratio and based on the demand.
You can control.
That is
We can switch off the flame whenever we want. In the other case, there will be a lot of.
You can turn off with a valve.
yeah.
But there. Will
Okay,
be
one thing what sir pointed out is important. You can locally very fast adjustment of equivalence ratio can be made. If it is in a big tank, then it will take quite some time to adjust things.
In aircraft, you cannot have a separate tank.
So these combustors are used in aircraft. It is not a premix flame, by the way. It is a diffusion flame, and what is burning there?
It's a liquid.
Liquid fuel. So we are not talking about that. We are talking about gas burners which burn natural gas or whatever other gas is available, and so it's mostly a gas burner, or even if it's a liquid fuel, we are talking about you can actually have injectors here pre-vaporize the liquid. So LPP stands for lean premix pre-vaporized also. So or you can have natural gas coming, one of these things. So why are we not calling diffusion flame or non-premixed flame? And you said it is because we are mixing it in this tube. So I think safety is the predominant thing. I think because it burn several. I mean it's they burn a very large amount of, I mean several kilograms per second to even perhaps big ones may burn I mean hundreds of kilograms per second or even tons per second. So it's a lot of mixture, and if you have a big cylinder which is I mean you have to pressurize it, because otherwise you cannot store. Storage volume will be very huge, and then if you have explosion, I think then it is, I mean it's unbelievably damaging. Or even if you can have protection and all that, still I mean this thing is going to go away. So this is called industrial premixed combustors, or the Germans call it technical. A lot of Germans worked on this. German, Swiss, Alstom is a Swiss company, so they call it technically premixed combustor. That's a German English. It's like Germans call technical aerodynamics. That means industrial aerodynamics. So but that's the name is there in English now. So it is called industrially premixed or technically premixed. So by the time it comes here, it's like premixed. So I hope this is clear. So the fluctuations in equivalence ratio are created by or generated by the acoustic waves. They are here in this combustor, they travel upstream, they come here. So that's what I denote by Pi and Ui. So some of the waves come here and then they modulate the fuel and air. So how does it physically modulate the fuel flow rate? Anviksha already answered it. Can you repeat the answer again, Anviksha? How does is it the velocity or the pressure which modulates the fuel flow rate? Why does it do it?
Sometimes it will make more fuel faster, sometimes it won't.
When is more fuel coming and when is less fuel?
When the pressure goes to a minimum, it's going to allow more fuel to come.
Okay, so when pressure here is low, you have a higher delta P you are putting in it, and so there is more flow rate coming, and when you have a higher pressure, when the acoustic wave is having a maxima, then you have less pressure drop, so then the flow rate will be less. So if you are thinking quasi steady, then the fuel flow rate will oscillate like square root of delta P approximately. When would this mechanism won't work? You can have, huh? Why choking will lead to no oscillation?
So any downstream
It won't be conducted.
Yeah, it won't go inside because your flow is coming sonic, so somewhere, and then so this perturbation cannot proceed upstream, and therefore the flow rate cannot change.
Sir, but pressure difference is what directs the flow rate, mass flow rate.
Yeah, what is the formula for so m dot stroke CHOKED so it is actually there are some factors 2 over gamma by 2 over 1 plus gamma per some gamma plus 1 by gamma minus 1. I don't remember the factor, but do you remember any? Okay, but there is a constant times P naught A star over square root of T naught, so it is P naught, but under incompressible flow situations this whole thing can be written as square root of goes like square root of delta P effectively. Okay, so now when you go to Mach 1 and so on, you have to use this formula. And why would the air flow rate oscillate? We have a very good explanation for fuel flow rate oscillating. Why is the air flow rate oscillating? Why is the m dot A mass flow rate of air oscillating? Huh?
U prime.
U prime. Why?
Mass flow rate is proportional to.
Yeah, mass flow rate is proportional to U prime. M dot is rho AV. That was the formula we remember, and we don't say rho AV is constant. You say if rho AV is the V is fluctuating, then m dot is fluctuating. Absolutely. So we have both the velocity fluctuations and the pressure fluctuations. Both of them are important. One causes velocity causes fluctuation in air flow rate, and pressure fluctuations cause fluctuation in fuel flow rate. Okay, so write down a few things. This is the rho C times S is the flow rate consumed, and I mean delta H is the heat of the reaction, and because your equivalence ratio is phi, only phi times delta H will be released. So this is the formula for heat release rate per unit area. Okay, we'll call it Q dot. So rho C is density of incoming mixture, S is flame speed, phi is ratio. I did not write SL, I wrote S. So combustor need not have laminar flame. Surely industrial combustors would not have laminar flame. So if you are talking about a linear system. So so if you are talking about a linear system, q dot prime by q dot bar is rho c prime by rho c bar plus phi prime by phi bar plus s prime by s bar. So if you are talking about low Mach number combustors, in aero combustors I think Mach number will be somewhat high, 0.2 or 0.15, 0.25 and so on, but in this domestic burners or industrial power generators flow will be very low. So under those conditions this may be negligible for low Mach numbers. So we will drop this and we will keep this. So we will so CD is the discharge coefficient, and you can, for low speed flows you can write this formula, and so delta P prime is like minus PA prime, assuming that neglecting the fluctuations in the pressure in the fuel line. So then m dot f will be proportional to u, so you can say m dot f prime by m dot f bar equal to minus pi prime by 2 delta p. So if you take log and differentiate, you can get delta p by p goes like 2 delta u over u, so that is where you get this. Now we will look at total equivalence ratio. I must emphasize that although this is at the inlet, but if you think about the pressure at the combustor, then it is actually coming after a delay time of t minus tau, I mean delay time of tau. So minus u prime of t minus tau divided by u bar. So this is the fluctuations in velocity at the injector. So because of the fluctuation in velocity, sound has both velocity and pressure fluctuations. So when the velocity fluctuates, if the velocity is increasing, the airflow rate will increase, when the velocity is decreasing, the airflow rate will decrease. So that also causes the oscillatory airflow rate. So together they contribute to equivalence ratio fluctuations. Okay. So yes, the flame speed depends on equivalence ratio. I can say S is in general, there are various correlations, but some of them are of the form S is proportional to phi power a. So ds over s prime over s bar is equal to, you can do some simple differentiation and derive this, have it here, but you can try this at home. So you can take log s is a log phi, then s prime by s goes like a phi prime by phi bar, very simple. So q prime by q bar is 3 prime by phi bar plus s prime by s bar, which is a phi prime by phi bar, which is 1 plus a into phi prime over phi bar, and this a can perhaps be somewhat large near the lean limit, and therefore for a given phi prime by phi bar you may get large q prime by q bar because a is larger than 1. So we know a relationship between dots heat release fluctuations and equivalence ratio fluctuations, and we know how equivalence ratio fluctuations depend on the acoustic fluctuations. We just derived this relation. So if you substitute this into this, you have the final answer, and so this in harmonic domain it will be plus a. No, sorry, I must keep the subscript I here. This sorry, I made a mistake. Not really a mistake. So the pressure at the inlet affects this, and then so you have a equivalence ratio fluctuation. It takes certain time t to get convected here, and only after that it burns. So therefore you have the fluctuation here, and it travels this distance by a convective time delay, and then it burns. So that's so the tau comes from the delay or the time for the mixture to reach the flame. Okay, so I'll
And here order of tau will be velocity.
yeah, it's the order of convective.
L by u.
Yeah. Well, yeah. Okay. And pi will have a relation to p which is order of L over c. So the total thing from with respect to the pi will have a delay with respect to p, as in so pi is delayed with the combustor pi p to pi would be like c over L over c, and pi to p would be of that's back would be the order of L over u. So L over c plus L over u, which is L over u into u over c plus 1, right? So L over u into 1 plus m. For m is small, it will be of the order of L over c. If m is small, then m is, let's say, 0.01 or something, then it's L over u times 1.01, so it's close to L over u. So So as I give you a reference, Louis Wind's PhD thesis, there he has worked out examples with various time delays between process and heuristically calculated when things will become unstable, when things will become stable, even before he does this calculation of eigenvalues and so on. So I think it's a good exercise to walk through that. Answered your question?
Yeah.
Okay. Speak loudly so that the question. Oh.
Yeah. This is not related to this.
Anything?
The acoustic flow, is it generally laminar, or it can there be turbulent acoustic flow? The U prime.
Yeah. So this is a very tricky question. So what is turbulence? It comes to what is acoustics, and so on. But people have. So it all depends on what you see also. So when you scale at so if you have hydrodynamics and acoustics decoupled, then there is no problem. Hydrodynamics has turbulence and we have low Mach number, acoustics is not coupled, but then they are coupled. So if you, the way to see acoustics would be you do some phase locking or conditional sampling, and you know the acoustic frequency, so you look at the signal at various times and then reconstruct the signal together, and then so let us say we have a reference signal somewhere here, we have a reference signal which keeps repeating. So I take values at this phase, I take values at this phase, I take values at this phase, here, 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 and like that all over. And then if you construct the velocity from this bin, so you will actually have, if you look at the velocity, it will have lot of fluctuations riding on a mean. So you have a, let us say, a clean pressure signal, or you can even turn on a you can take a tube, connect loudspeaker to this combustor and drive it with some sine wave and all that. So let us say we phase lock the signal with that. I have seen some experiments like this, one of my friends used to do, and you would see a lot of fluctuations on top of this signal, which is phased averaged at the acoustic period. So could you call this turbulence? Perhaps, but I mean that's difficult, is probably because we can't quite separate under non-uniform flow and under heat release fluctuations. Hydrodynamics and acoustics are very coupled. So what is acoustic would be like you average everything which are one second, let me see how you average all the fast scales, and then you see hydrodynamics, and you in space you average, and then what you see would be like acoustics. That's one crude way of answering, but I think we have.
Which is of the order of acoustic, like velocity of sound will be acoustic.
No.
Which has a time.
So
velocity.
I think what you have to do is if you are looking at the thing theoretically, you have to look at the eigenvalues of the operator, linear operator, and if that is C, and then you can call that fluctuations and acoustics. So if it is experimentally determined, you have to, let us say, put pressure probes at two locations and do find out, you cross correlate them and see what is the delay between them, and if that is speed of sound, then you can say okay, there is something acoustic to it. But this could be mixed modes, and I think these are not analyzed. I mean, it's all topic of current research, so I can't give a proper answer, but this is like a half-baked answer, but this is a very good topic to do research on. Okay, any other thing?
But an acoustic field doesn't have a convective mass flow, so you can't actually talk about laminar and turbulence.
A purely acoustic field cannot have any of those things. So here we are in general you have acoustics which we learn in first class, and then you learn fluid mechanics and so on, but this is thermoacoustics is where then acoustics is coupled to hydrodynamics because of the non-uniform flow or heat release rate. So then these eigenvectors, which are originally distinct, but now the energy of the system is not energy in acoustics plus hydrodynamics plus entropy, but plus some interaction terms. So this interaction comes because of this coupling. So in the frequency domain this t minus tau will translate to e power minus I omega tau.
Between 0 to 1.
A can be higher than 1 if you as you go towards the lean. I don't often remember the value, maybe I can tell you next class. So we have a time domain, we have a heat release expression in time domain, we are expressing for heat release in the frequency domain, and now we have two different methods of analysis, one in time domain and one in frequency domain. So plug this in and then we can calculate our eigenvalue or a time series and so on, and then you can look at the eigenvectors or you can see your evolution of the system and so on. Okay. Now let us look at some numbers. We look at a choked inlet where there is no fuel flow fluctuations. This is an example given in Loewen's thesis. So no fuel modulation, phi prime by phi bar equal to so let us look at how these numbers are for a u prime by c bar is 0.01 for a 3 meter per second fluctuations of that order, and m bar will be 0.05 when ui bar equal to 15 meter per second. If the flow rate is if the flow velocity is 15 meter per second, then m bar is 0.05. So phi prime by phi bar is of the order of 0.01 by 0.05 equal to like 20%. So you can have substantial phi prime by phi bar, and that can lead to substantial heat release oscillations. There is one more issue that is involved here other than this instability leading to oscillations. So when you have very large amplitude oscillations and you are at the lean blowout, now the flame whether it stays or not depends on whether locally somewhere the radicals are there and you are having the flame velocity match the flow velocity, but then if you have very large amplitude oscillations, flame may blow out. So lean under very lean conditions, these thermoacoustic oscillations can lead to lean blowout. So we can't quite operate the combustor as close to the lean limit as we want, because we can blow out. So you will have to always have a factor of safety where the oscillations don't trip the flame to have blowout.
In this case, even there can be situations where the mixing becomes improper because of the acoustic.
Mixing becomes?
Because here there is that duct in which mixing happens.
Yeah.
And the blow off can be because the mixing is imperfect.
Mixing will be very good actually, I think, when there is acoustic oscillation, so that is not the reason, but I think the stability itself will be altered. So blow off happens when yeah, I think it needs some elaborate explanations. I will not get into it, but I think the flame cannot be stabilized under large amplitude oscillations. Huh? Will be much better actually. Okay, so that is not the reason. Any other questions? Okay. Thanks. Go.